Good evening, everybody. So today we have a very interesting talk by Sergei Gukov, who is a professor in California Technological Institute, and he will talk about the application of reinforcement learning to mathematical problems. Sergei, thank you very much that you agreed to make a talk, and please start.
Well, thank you, Sasha, and yeah, thank you for inviting me. It's actually great to reconnect. So Sasha and I were students together when I think at least I was making my very first steps in mathematics, well, professional mathematics, I have to say. So it's actually a pleasure to see old friends and many new faces. So yeah, thank you for having me. I know Sasha is the boss and he muted everybody, but I do encourage questions. In fact, as I mentioned just before the recording started, that I'm not sure what the right level is. I'll answer some questions, including how I got into this and so on. And I try to be fairly elementary, but if you want more technical details or on the contrary, want to clarify something, feel free to ask. So please utilize this option that Sasha offered, writing it in chat or ping him to unmute you. I definitely encourage all of it. Right, so maybe let me try to explain how I got into this, since many of you know me and yeah, as you say, how on earth it happened that I got into this. Basically, about 5 years ago, when it was already past AlphaGo and AI was already in the media, quite popular. Maybe not as hyped as these days, but still it was definitely in the news. I asked myself, okay, that sounds fun, but can it really help with professional high-level mathematics? Something that can replace me as a researcher level mathematician, for example. Can it solve very serious problems? And I did one project with my colleagues. I'll mention that project in the process of this presentation. And some of my colleagues were new to this, some were already quite experienced, and I'm very grateful to them for sort of introducing me to the field. And my goal in that project was basically to try to assess how well can it do. And I was very surprised that AI did 10 times better than I can do by hand. And I'll quantify what this means in a second. But this basically told me, okay, I have to take this development in AI very seriously, that if it can help me with professional mathematics by a factor of 10, nothing is stopping us from improving it to 100 and 1,000. And I'm not only talking about algorithmic improvements, which is what I'll try to sort of focus on throughout this talk, but this is an interesting aspect of human versus machine kind of comparison, that as a human, when I'm working on mathematical problem, it's almost impossible for me to improve my performance by a factor of 10, 100, 1,000 tomorrow. But for machine, it's actually a reasonable question, because if you know how performance scales with, for example, number of GPUs or nodes or memory used, other resources, we can simply allocate appropriate resources to accomplish 100 times improvement or 1,000 times improvement. So this is a bit different from human performance. If I have one student, I cannot ask that student to perform as 1,000 students tomorrow, but with machines, we actually can. And it's just a question of doing back of the envelope calculation to allocate resources. So this was very, very interesting. And basically, that's one of the reasons why 5 years ago, I started taking it seriously and said, okay, I have to learn the subject, and learning is fun, so why not? So then I'll tell you the rest of the journey later. So indeed, as Sergei already pointed out, in the past, before sort of pivoting in this direction, I was doing some version of quantum topology. And I'm still very interested in quantum topology, but I can now try to quantify what I mean by 10x improvement. So those of you who are familiar with quantum topology or knot theory know that questions boil down to concrete computational questions, something like computing, say, Jones polynomial or some other quantum invariance for knots. And in this subject, the natural measure of how complex the problem is the roughly number of crossings in a knot diagram. So that's the horizontal axis on this plot. And most of practitioners, at least like myself, when we do calculations by paper and pencil or using traditional techniques and computers, we stay in the range of very small number of crossings, by which I mean roughly 10. Very few people venture beyond, say, 16 crossings. And this diagram shows that at 10 crossings, you only have 165 prime knots, which is a pretty big number, but it's not huge at all. But this number grows very fast, factorially or exponentially, simply because each crossing roughly introduces a binary choice. So it should scale roughly right, like 2 to the n. Of course, this is very basic estimate, but it's true that it grows exponentially. And at 16 crossings, for example, you already have more than million knots. And beyond 20 crossings, they're not really even classified, so they don't have names. But what was frustrating to me as a working mathematician at the time is that to solve interesting problems in topology, so quantum topology doesn't really have many topological applications. So that's basically the challenge or bridge that I was hoping to build or help to build. In topology, we have problems which are, for example, one of the most famous one is probably smooth Poincare conjecture in dimension 4. But then there are many other interesting problems. So in 1962, Ralph Fox introduced so-called slice ribbon conjecture, which says that every slice knot is a ribbon. The converse is obvious, but it's actually highly non-trivial that slice knots are ribbons. So this is something I might touch upon a bit later. And in my mind, this is also just as interesting as smooth Poincare conjecture. And there are many such conjectures in low-dimensional topology, which are open for more than 60 years, and where we have no clue at present whether it should be true or false. So to me, this is quite exciting because, for example, in P versus NP or Riemann hypothesis, we know what to expect. And in a three-dimensional version of Poincare conjecture, we did know what to expect. It was just that we were missing the proof. But 90% of the community would agree that it should probably go this way or that way. But the conjectures I'm mentioning here in low-dimensional topology or knot theory, what makes them interesting to me is that we actually don't know. So they can be true, they can be false, but despite decades of attempts, we didn't actually make enough progress. And to me, as a working quantum topologist, it was very frustrating that quantum topology produces zillions of invariants labeled by groups, representations. It utilizes very advanced representation theory to produce new invariants, new topological invariants. But how come this new topological invariance shed very little light on many of these open questions? And part of the reason is that to answer some of the topological questions, we need to work with pretty high number of crossings. So some of the potential examples or counterexamples in this field start with, as this graph illustrates, at 70 crossings and up. So the smallest example is 48 crossings. So this is to the slice ribbon conjecture. In fact, Gomb, Charlemagne, and Thompson, whose images you see on the slide, produced the whole family of potential counterexamples, and 48 crossings is the lowest member. The next one is much higher, already in the range of 70, 80, and then they quickly go above 100. So there is a huge gap between what we could do, or I could do 5 years ago with traditional computers, and what I would like to do to rule out some of these counterexamples. Basically, to rule them in, I would need computational power, which would allow me to work with hundreds of crossings, whereas traditional computers would basically stall at, I don't know, 16, 20 crossings. And the problem is quite serious because not only the number of nodes grows exponentially with a number of crossings, but the amount of time you spend on computing invariant for a single node diagram also grows exponentially with number of crossings, because if you compute it using some R metrics or other technique, you basically have fairly complicated metrics product type operation for each crossing. So therefore, complexity is exponential in number of crossings. You have to do some summation for each crossing. Right, so that's the TQFT aspect of it, which was basically producing this exponential growth of complexity. And then I realized that okay, that's fine if we can do, for example, 16 crossings today. According to Moore's law, computational power improves on traditional computers by, let's say, factor of 2 every year. So that means that computational power is growing also exponentially. But then we are comparing two exponentials. And if last year we could do 16 crossings, it means that next year we can do 17 with this improvement of technology using traditional computers. 2 years from now, we'll get 18 and so on and so forth. But if I want to get in the range of hundreds, I have to wait 50 years. And my problem is that I don't have that much time. So I would like to battle this exponential growth much faster. And that's exactly the factor of 10x that I had on the previous slide that got me into this game and justified that, okay, I have to take it seriously. Okay, so another aspect that I want to kind of cover is that I'm talking about research level mathematics problems, something at the level of Poincare conjectures or conjectures which are open for many decades. A year ago, I got involved with one of the Silicon Valley companies to solve IMO problems using AI, and I'm still working with them, but it was actually a fun decision to make a year ago because a few months later, in the fall 2023, XTX announced this 10 million prize for AI solving IMO challenge, and I'm pretty sure it's going to happen in 2025. In fact, of course, I'm rooting for our team, but I suspect that several teams may get there. And the progress is going well. So, for example, this screenshot from Kalshi is taken in spring of this year, and you can see that from March to April to May, performance improves roughly by 5% every month. So if you extrapolate till next July 2025, you'll probably get there all the way to almost 100%, which is what you need to get gold on IMO challenge next year. And I'm very optimistic that this is possible. Again, I cannot really tell what we're doing because this is a private company, but what I can tell you is that I'm confident that it's going to happen. And part of the reason is that these are simpler problems. And even as a kid, when I was in school, I loved these Olympiads, and there was a very straightforward way to approach them. We just, in a boot camp manner, we would practice. And after a while, if you practice enough, you realize that, first of all, there are like, I don't know, 20 or 30 or 50 types of problems. Once you see a number theory problem, you immediately start trying a palette of like traditional strategies or ways to approach it. There are also many analogous problems on which we would train back in the day when I was a kid. I was also training various teams later. So now training AI feels very much like that, because what AI does at a very basic level, it's just seeing many iterations of the same thing and improves performance from these iterations. So I want to emphasize that this is very different from research level problems that I'll try to describe on this talk, because we don't have that many solutions to Riemann hypothesis. We don't have that many textbooks which solve problems analogous to slice ribbon conjecture. In fact, we have none. And the fact that we don't have a specific solution to IMO problem from 2025 is not much of a problem because we have lots of analogous things in the same vicinity and a lot of training data. And clean data is very important for AI. But for high-level research math, as I'll try to explain later in the talk, this is not the case. And that's why I want to contrast what I want to discuss in this talk with much easier goals in my mind, which are high school mathematics, Olympiad mathematics, or even undergraduate level mathematics. So that's much, much easier simply because we do have access to a lot of clean data, but not so for, say, Millennium Prize problems. Okay, assuming that there are not everyone is an expert on reinforcement learning, I'll also try to give you in this talk introduction to basics of AI and reinforcement learning. So now as we slowly learning that it could be useful, so what's there for grabs? So there are many extremely good textbooks, and this picture is taken from one of them, which describes artificial intelligence according to this sort of Venn diagram, different areas, what it does. And when I was introduced to the subject, I was working solely on machine learning. And I thought that artificial intelligence, which is a broader term, includes all kinds of things which are too philosophical by my taste, such as reasoning and cognition that machine learning does not include. And I thought that I would probably never venture in these areas. But actually, what I want to get to in this talk is eventually I basically did, and I think that's pretty exciting and interesting. But for most of this talk, I'll focus on machine learning, which is sub area of artificial intelligence, which is basically focused on analyzing data. And I think there is either comment or question in the chat. I see there is something, I don't see what it is, but.
Yes, there is just a comment. So just a moment. I've been trying to use ChatGPT as tutor for topological quantum field theory, but it can't even calculate Wilson loop for abelian version of the Chern-Simons. That's where the Gaussian linking number should come out. That's not a question, just my musings. So it's more a remark.
Right. So when I talk about AI, unfortunately, ChatGPT won't do it. So ChatGPT is a very no offense, but it's to OpenAI, but it's for mathematical reasoning. Of course, it's not a device. I mean, it's yeah. I wouldn't even I personally I don't use it even for my own writing. So I know that it can write pretty good text, but yeah. So I mean, that's not a serious tool, unfortunately. I apologize. Yeah. So we're going to be talking about, yeah, so we'll have, so when I started on this, I really had to learn how to code in Python, write code, and what I'll try to describe in this talk is actually what we'll need is to build our own algorithm. So we cannot just take something off the shelf and especially something as primitive as ChatGPT and expect it to work on anything research related. So yeah, no illusions there. All right, so moving on to machine learning. So I want to tell you a little bit about machine learning. So getting to what this talk is really about. So it's not about elementary problems. Actually, ChatGPT may do well on maybe not high school, but maybe elementary school mathematics, or maybe middle school. I don't know. I don't know where the level is. But this talk is not about Olympiads. It's not about undergraduate. It's about much more challenging research level math, something I want to do as a professional or improve my performance by 10x or 100x. So for this, we'll need machine learning. In fact, we'll need a sub area. So I'm slowly zooming onto what we're going to need. So there are three broadly defined areas of machine learning. There, of course, classification is maybe a little idiosyncratic, but I think it's a fairly traditional way to describe it, that there is so-called supervised learning. So that's the branch of machine learning that analyzes labeled data. Unsupervised learning techniques like clustering and so on is all about unlabeled data. And reinforcement learning, that's actually what we're going to focus on, is the branch of machine learning that is trying to play the game, roughly speaking. So you should imagine that there is an agent which tries to make various moves. Again, think about board games like chess and Go, or this lunar lander computer game that you see on the screen. And based on its performance, it's learning from previous iterations to improve the policy or how it should make choices. So it's all about improving decision making, something we do in real life very often on a daily basis. And actually, that's exactly how we learn to solve Olympiad problems as kids. We train, see how we did. We learn the lesson, something that good. We say, oh, okay, let me keep it in mind in my memory. That was very useful technique. Something that doesn't work, we also record and say, okay, I shouldn't try this next time, and so on and so forth. That's basically how learning is done. And reinforcement learning is basically this branch of machine learning. So this is what this talk is going to be about, reinforcement learning. At least I'll start with this, and then we'll see how AI comes in naturally. But this is, of course, part of AI. Okay. So when we make decisions, it's good to think about a complexity. So in computer science, when we try to devise algorithms, it's good to do back of the envelope calculation to see how hard or easy our problem is. For instance, if we think about going from A to B, from start to finish, or for cat to find the milk or go through the labyrinth, as in these pictures, it's good to think, how many options do we have? So what is my space, exploration space? Because that's basically what our reinforcement learning agent will have to explore. If we play moves in a game of chess, we have to know roughly, first of all, how long the game is, and secondly, roughly how many moves, how many choices can we have for each move every time. So this talk is actually based on a paper that I think is linked to the abstract of this presentation. And there we managed to solve a very important, interesting case of Andrews-Curtis conjecture. I'll talk about it a bit later. And to solve it, we had to make more than 50 moves. And each move involved 12 choices. I'll be able to explain where 12 comes from and so on. But it gives you an idea that if it's length 50 or more than 50 and 12 moves, it means that the agent had to explore or make choices on the length of 12 to the power more than 50. So that's a lot. It's essentially 1 with, I don't know, 60 zeros or something. So that's a huge space to explore. And it doesn't need to be manageable, but it's always a good idea for you to, when you have specific problem you want to explore, to estimate the complexity. So I already alluded that in a study of knot theory, complexity explodes exponentially, and we kind of did this back of the envelope estimate, and it's always a good idea. So part of the reason is we have to know how likely are we to find acceptable solution. For example, if we go over this 10 to the 60 potential configurations, as we had to do in Andrews-Curtis conjecture, I will looking for majority of the answers, unique answers. So we need to know the estimate, like to get an idea of what's the probability of winning the game. So that's always good. And again, I want to encourage you to think about such problems. A simple exercise could be, for example, that's not even an Olympiad problem, it's a basic math problem. Suppose you have a mouse which moves, it makes only 2 moves, goes to the right or down on a square grid of size n. Natural question is, how does the number of potential paths scale with n? So that's a very simple question. But next question is, suppose your space of actions, the number of moves you take, increases. For example, instead of 2 moves on 2-dimensional plane, it actually moves on three-dimensional grid, and there are three choices. So it can go left, down, or in a third dimension. And yeah, so how would be what would be the scaling with n? And of course, you can extrapolate this again, do a simple back of the envelope calculation. Suppose your action space is d-dimensional, size is roughly n. So how does your number of choices scale with n and d? So that's the kind of thing that computer scientists do all the time when they try to think about, even before they start doing reinforcement learning for real. But it's a very good idea to get this estimate. Okay, now these days there are many interactions between mathematics and machine learning, and first one can try to be very utilitarian in the sense, just try to use machine learning for mathematics, proving or disproving conjectures, using supervised or unsupervised learning to make new conjectures, and so on and so forth. So that's the box on the top panel. In addition, actually, there are many ways in which mathematicians can be helpful to AI by trying to white box current models, including transformer. T in ChatGPT or GPT stands for transformer. That's one of the most complex architectures, and there is a lot of effort is going these days into understanding how it works, why it works. There are many things that we still don't understand, not only in transformer, but in many other models. And mathematical tools actually could be super helpful there, and that's the box on the lower left. And another branch which already had life of its own is basically auto-formalization and proof assistance. Languages like Ling, Coq, Isabelle, and others allow us to formally verify informal proofs. So papers published in Annals and Vinciani's top math journals are still considered informal. And sometimes we know that later corrections surface and some of the proofs which were accepted in these journals are incorrect because, again, they're only human verified. So it would be good to have complete absolute verification by software such as, again, Lean, Isabelle, or Coq, or other languages. And these days, AI can be super helpful in automating that process. So this is actually a slide that I used from many years ago, and I used to think that these areas, of course, they talk to each other, they benefit from learning lessons in one, immediately provide some insight for the other. But more recently, especially based on this paper that we had very recently, I realized that all of these areas, not only they talk to each other, they're actually the same as far as biggest challenges go. So biggest challenges in each of these areas are actually deeply interconnected. In fact, it's the same challenge. So that's going to be goal of this talk to clarify that. So if you're not familiar with Lean, that's how it looks like. And Lean, again, is a formal language. It actually, just like Coq, Isabelle, and others, it can actually do some computations and used for programming. But I think these days, it's very popular for formal verification of informal statements. And it's actually very challenging language, I have to say. So among things that I ever had to learn, this is probably most difficult, at least to me personally, because it includes all kinds of syntax, tricks, and other things which I don't find very intuitive. Terry Tao is one of the few professional mathematicians who is using it. And I think his quote at some point was that it takes him roughly 7 times more time to write a proof of a theorem in Lean compared to just informal proof. And that definitely echoes with my experience, which is not entirely positive. So it is uphill battle to construct these formal proofs, and it's a slow process. There are many libraries. One of the most popular is MathLib, which is constantly growing thanks to work of many enthusiasts. But it's very slow. And this last year, I was teaching a course in knot theory. So I thought, oh, maybe let me try to at least prove or give a in-class version of the first theorem or lemma in knot theory using Lean, and I couldn't do it simply because knot theory does not exist in Lean, or at least it was not part of MathLib a year ago when I was teaching this course. Maybe now somebody wrote a few basics there, but it's a slow process, and again, many areas of mathematics are simply not represented and need time and so on. So that's where AI will come in and help. But part of the reason I'm holding the slide here, I want to illustrate more successes of Lean and how it works. And as you can see here, some of the basic theorems, actually, if you Googled like main theorems in math and Lean, you can probably find even this side. So some of the proofs are not too long, and they take decent number of steps, which you can see here is on the order of 10. So that's not hard. Oh, this is a nice anecdote that, yeah, so when people started formalizing mathematics, of course, they also formalized Euclid's elements. And that's actually, so this slide is meant to illustrate why it's useful to formalize mathematics, because of course, hopefully nobody in this audience doubts that Euclid's elements are valuable, correct, and so on. But when we prove things, we sometimes say that, oh, we prove only one case and other cases are analogous. And this is a legal thing to do when other cases are really symmetric. I mean, that they're really mirrors of whatever we showed. But sometimes they're not. And that's actually the case with one of Euclid's elements, which was found a couple of years ago when people were trying to formalize this. And yeah, Lean community knows this quite well. So this is a nice anecdote where even something as basic as, again, Euclid's elements may turn out to be not formally proved, simply because Euclid assumed that the other case is similar, but it's actually not quite symmetric. So we have to be careful. And of course, people like Peter Schulze and Terry Tao, they point out that in even professional mathematics, they find lots of small mistakes in their informal proofs when they try to use Lean. So there is a great value there that you try to be careful and very essentially have a proof on Lean that has no sorries, closes, that everything is green in the info view on the right-hand side. And this leads you to understand better even the theorem that you're trying to prove. So that's actually quite valuable. So maybe I should point out that again, think about reinforcement learning and how AI could help with the Lean proofs. So I mentioned to you that reinforcement learning is basically training the agent to go from A to B. And when we're trying to prove a conjecture, say one of these conjectures like Riemann hypothesis or simpler conjecture, or maybe theorem from our daily life, we're trying to go from hypothesis to the goal. And in Lean, it's very specific. You basically have to make certain number of steps to go from from hypothesis to the goal. So that's very much like what general reinforcement learning agent is doing. It's pretty much the same. And that's the sense in which I meant that many of these problems, whether you're trying to use AI to help formalization of proofs or white box some of the AI or use AI to prove or disprove conjectures, actually in many levels it's very similar because problem boils down to connecting A to B or goal to hypothesis to the goal, and you have to make certain number of steps. And in fact, by now I have several projects which are very far from my field of knot theory, quantum topology, which I'll use as examples in this talk. For example, recently we started new project with David Eisenbach, Paul Orland, and Hao Long on commutative algebra. So with Kirill Brylyantov, who is here on the call, we started exploring Kazhdan's property T. And these are completely different projects from many different areas, but many of them can be formulated as a game or as finding a path from A to B. And that's exactly what reinforcement learning does. And that's also what you would need for AI-assisted lean proofs. And in fact, to me, now this is kind of a little sad, because whether we're trying to prove a conjecture, disprove a conjecture, prove a theorem, problem always can be reduced to some form of connecting A to B by a sequence of basic moves. So if anyone has an example which doesn't look like that, or if you have a favorite example which does look like that and you want to explore it, please feel free to reach out to me via email, or after this talk we can chat and discuss. But it's kind of sad that much of mathematics, whatever the problem is, it doesn't even have to be from our native areas, can be formulated in this way, as going from A to B via, and then finding the path is the main challenge. So that's going to be the main problem that we'll try to solve. So maybe I should pause for questions at this point.
Colleagues, so please don't hesitate to ask questions. Maybe I'll try to allow to unmute because I think there are no Zoom bombers. Just a moment. Let's try. Hope there are no Zoom bombers. So, any questions, remarks, or whatever? Well, first, for me, it's very interesting, a little bit unusual what I hear. So what you say is that in what generality do you expect that all the math problems is just find from A to B? Because, well, I know some several problems, but I didn't thought that it's very general.
Yeah, so again, I don't want to, maybe, yeah, I'll encourage discussion over email or maybe after that. But surprisingly, most problems that after some thinking, so it's not maybe immediate, but for example, proving a theorem is definitely A to B. Now, proving Riemann hypothesis, definitely A to B. We know what the hypothesis is. We know what the goal is. We just need to find a sequence of steps which connects us, right? So many counterexamples to conjectures, this is something that I'll try to illustrate maybe later in this talk, is also A to B. So surprisingly, thinking about it for some time usually reveals that pretty much every problem, at the gist of it, is finding a path that connects hypothesis to goal, or A to B, or so it's basically all about finding path. And then we can transition to AI by trying to start optimization on clever choices of what the action space is, what should be the space of states, so that it's better or easier for agent. But to me, it's a little, yeah, surprising to myself. I agree with you that it's a little unusual that much of math, much of what we're trying to do, at least research level, can be formulated as finding a path. And to me, this is kind of also sad, because it means that, yes, AI will definitely help with this. Question is it going to be in 2 years, 5 years, or 10 years? But that's exactly what reinforcement learning basically does. It's finding a path. Yeah.
I have a really quick
Sergey,
comment. Oh, sorry. I'm sorry.
Yeah, go ahead. I'll ask next.
No, I apologize. I just had a really quick comment. Like in the history of math, though, sometimes I think this characterization works if the definitions and everything is fixed. But like in the history of math, there's been cases where there were mathematicians working on a problem and they refined the definition to achieve a solution. I mean, that's obviously trivial, but I'm kind of curious, like in your system, would it be robust even for me to try to change the predicates or the definitions and then it just becomes like an A to B problem, I guess? Or am I saying something ill-defined? I'm sorry if I
No, you're not. It's a very good question. I hope I'll get to this in this talk. So my point later will be that AI systems that we really need for solving, say, Riemann hypothesis will definitely have to do this kind of things. So they definitely, in other words, they'll have to think outside of the box. And that's in some sense the main punchline of my talk. So I hope I'll get to that. I don't know if Sasha will allow me some extra time. I'm trying to go super slow, and I realize I probably will be way under. But yes, you're absolutely right. And some of this is already happening even in more basic systems. For example, those which try to solve Olympiad problems. So this was already clear with, say, alpha geometry and many others. They do have intermediate constructs, which are basically definitions. And they see that, oh, introducing some intermediate definition is very useful for blah, blah, blah. I mean, it's could be approached from a number of kind of perspectives. But I would say that that's still inside the box because it's a definition not too far from what we had. But I would be totally with you that constructing definitions in a Grothendieck style, which is introducing something that we didn't even think, I mean, it doesn't look close to what we had before, is going to be crucial.
Yeah.
Sergey, can I ask a question, please?
Yes, yeah.
What about computational problems? Suppose we want to find the solution of differential equation or compute cohomology of a certain group. How it fits in the frameworks for going from A to B if we don't know the B yet?
But so that's a very good question. We have to, let's discuss this after. But suppose you are to finish your computation and submit a paper in Inventionis. So eventually it has to be a proof, right? So
No, of course. If I know what I
right.
should get in the end, then
So
yeah.
right. But so let's just backtrack this process. So how does it work? You have to have some kind of, so before you write it as a proof, what we call computation is basically formulating a conjectural proposal, right, for what the answer is. And then we're trying to justify it a little better, more rigorously, and so on. And that's also something that AI can, of course, help with, formulating conjectures, proposals, or extracting structures. So on purely computational tasks, I agree that I don't necessarily, I mean, usually some custom-made machines may be better and AI may assist them, but this may be domain dependent. So I think this is a very good question. That's why I'm super excited to discuss it. But I suspect supervised and unsupervised learning may be first necessary step to assist those computations. Not quite a realm.
Thank you.
Hi, everybody. Just a small question. Like 10 years ago, around that, Vladimir Voevodsky was a pioneer who initiated these activities with Coq and proof assistance. So the question is, what is the comparison with Coq and Lean? Is it just simple matter of translation, or there are some specifics using Coq and Lean building this?
There are. So there are slightly different.
Yeah, okay, thanks.
In fact, quite a few differences. For example, they have different functionality in terms of using them as programming languages, which I think will be important for some steps in research level math. But they're also similar enough. And currently, I think Lean, again, I may be very biased, but from what I see, Lean is leading in terms of, so the main question here is accessibility and size of libraries. Because as I mentioned, for example, knot theory was not in Lean at all. And the question is, which one is building with a faster speed? So I think Lean is slightly winning. Again, I may be biased, but I don't think we should worry about it because by the time AI systems, by the time we reach critical mass, and AI systems can do it fast and easy, this will be an easy translation task. And if we think about, say, ChatGPT or Claude translating them on 90 languages, this will be just like that. Currently, it cannot do it simply because there is not enough data to train on, and it doesn't have all the right libraries. But again, once the critical mass is reached, if you and I, for example, like to work with Coq and somebody wants Lean, that won't be an issue.
Okay, thanks.
So just a matter of time. In fact, this is going to be a very short time. That's probably going to be just a couple of years, I would guess.
Cool. Thanks.
All right, so I'll continue then. So yeah, so this is another example of, in fact, that was exactly my first example of trying to connect A to B to ask questions like, for example, is the diagram on the right same as diagram on the left for a knot? And this one has 10 crossings that illustrates the complexity. This is kind of questions where, again, our job is to try to train RL to go from A to B in answer question. Is a given knot unknot, for example? And yeah, here is an illustration that as number of crossings grows, it becomes more complicated. So it's much harder. Complexity grows exponentially. So, but that's actually perfect for RL. In fact, you would expect that it's simple for RL because there are essentially 3 basic types of moves. In knot theory, they're known as Rademacher moves. So this game is actually, if I phrase it as a game, should be easier than chess because it's like Atari game where you have only 3 motions of joystick, like up, left, or right, and yeah. So there are only 3 basic actions, and you can think of Rademacher moves being fairly easy. And yeah, so these are some of the projects that are maybe relevant by now. Like I say, I'm interested in many others, but one of my first was exactly this unknotting project where you see complicated diagram like the one on top right, and you have to decide whether it's knotted or unknotted. I know it sounds very silly, but it's actually kind of question that we need for this slice ribbon conjecture, Poincare conjecture, and many long-standing conjectures in topology that I mentioned earlier. So it's kind of, in my mind, perfect because it has huge impact on mathematics. And it sounds like a nice game for reinforcement learning. But something I didn't know before, and that's, again, I'm not sure if I'll have time, but I'll try to tell you that I learned something very important about algorithmic complexity and algorithm development by trying to think about this sort of problems using AI. So a version of this problem, which I already mentioned earlier, is a slice ribbon conjecture, determining whether knotted diagram like this is slice or ribbon. It's actually close cousin of unknotting because to these 3 Rademacher moves, you add one more move called band addition, and you basically get this version. And yet another version, which I'm going to focus on, is Andrews-Curtis conjecture. That's basically analog of this problem from combinatorial group theory. So this is the one which appeared in a recent paper with a number of authors. And when I give these talks, I usually want to advertise that I think it's important for our community to have all our results publicly available. Even though I work with Silicon Valley companies, I always root for open source codes. So we can proceed forward and analyze and help each other. So in particular, for the second version, I didn't get a chance to update the last one, but for the second version, you have GitHub repo where you can find code for sliceness or ribbonness, and you can actually start playing with it yourself. You can see that it works reasonably well for knots with up to 70 crossings and up. And this is actually much better than I can do as a working mathematician. Yeah, just maybe as an example. So Lisa Piccirillo in the past few years got very famous by addressing the Conway knot, which is only 11 crossings. So she proved that it's not slice. But yeah, so that fits very well in the description of the complexity that by hands or mathematical techniques, and these were actually quite ingenious techniques that she used. So we can deal with, I don't know, 10, 16 crossing, but what we need is many dozens for deeper topological applications. So anyway, when you train RL, for example, think about this lunar lander, which has to land safely, and there are just a couple of basic actions. You typically want to see graphs like this, where as process of training, your performance improves. And this is actual picture from our unknotting paper, where you see the performance getting close to 100%. And in the past, and also in textbooks on reinforcement learning, you usually want to see this and celebrate. And you say, okay, I'm done. This is great, great results. So it is great. I have nothing against it. But now I look very differently at these pictures. So that's going to be, in some sense, that's the goal of my talk. So in that unnoting project, so we did this RL training, and in particular, we used several off-the-shelf reinforcement learning algorithms to train the agent to do the unnoting. And again, you can think of doing the same for Andrews-Curtis conjecture, and we actually did use all of the above. And what you see here, for instance, is that so we used braid presentation for the knot, and as the braid length increases, you can see that performance actually changes. So some of the existing off-the-shelf textbook algorithms do well and some don't. And this is always a good thing in AI, to try different ways. And again, of course, this is much more sophisticated than just ChatGPT, which probably would not be able to do anything at all. So usually you compare everything to random walker. This is just trying to make moves at random. And not surprisingly, it's not going to do well, but you use it as kind of baseline comparison. So these are the green dots, which of course just plummet and nothing good comes out. So then there are a couple of other dots here. In orange is A3C. That's a very popular algorithm. I'll try to explain it in a couple of minutes. But as you can see, it also doesn't perform too well. So it actually goes down eventually. But TRPO, that's yet another one, does well. Okay, and this goes up. So this graph illustrates a couple of things for those who want to apply reinforcement learning to mathematics, or more generally. So first of all, one lesson that we see from this graph is that it's a good idea to try different things, right? Because, for instance, if we tried 5 algorithms which work like A3C and didn't try TRPO, we wouldn't get any success on this particular problem, right? So it's a good idea to try many things. But it also has another lesson. So if we think about it for a second, we immediately realize that what we are trying is something off the shelf, something from textbooks. And suppose you have a given mathematical problem. What are the chances that one of the traditional textbook algorithms, and there is only like a dozen of them, is ideal for your particular problem? The chances are strictly 0. Simply because in the space of all possible algorithms, we are trying 5, maximum 10 special points which have a name like TRPO, A3C, but what's going to be optimal for our complex problem is likely to be outside of this, I mean, somewhere else in the space of algorithms. So it gives us a lesson that custom-made algorithms for our particular problem are probably going to be much, much better than any of the off-the-shelf textbook algorithms. So this will bring us a little bit further to algorithmic development, but I saw that there was some either question or comment in the chat in the meantime.
There's a short question about this picture. Is there any explanation why TRPO might work better than in other?
Right. So there is an explanation. So this was, again, taken from the paper Learning to Unknot. So we offer some comments and explanation there. Again, in view of time, I probably won't be able to give you a detailed answer, but my main point is that in every problem, whatever problem we're studying, something like Andrews-Curtis conjecture, unknotting, or the slice ribbon, it's always a good idea indeed to do exactly that, to ask why some of the things do well, why some of the things not do well. But more importantly, already at this level, I can introduce more serious question and ask, then point out that if you want to solve really serious problems like Riemann hypothesis, Millennium prize problems, and so on, so I want to advocate, and that's the point of this more recent paper, we have to teach AI to do it automatically. In fact, on a very long horizon of training, we have to teach AI how to do this analysis, why something works, why something doesn't, so that not we do it as human expert, try to dig into this and analyze. And again, we did this for learning to unknot, so just look on the paper. But AI system has actually to be able to do that. Otherwise, we have no chance of solving Riemann hypothesis using AI or Poincare conjecture. So, or I mean, maybe we will, but some completely different ideas are needed. And in the beginning, I said that I didn't like that cognition and reasoning part of AI sounded too philosophical to me. But actually, what I want to point out is that this is the first hint that we have to devise algorithms that are able to sort of interpolate, if you wish, between TRPO and A3C. So these are some of the, again, traditional textbook algorithms. But what we need is a machine that's able to somehow interpolate, not just adjust hyperparameters, but really sweep the continuum of algorithmic space to optimize its own used algorithm for whatever complex problem we're trying to solve.
Sorry, any idea this interpolation can be made with within the current technique or something like gradient descent methods, or it's requires something completely new? So what's your
I think
take?
it requires, yeah, so what I'm trying to advocate for is, of course, a fantasy. So this interpolation does not exist. But in my mind, it's exactly this kind of interpolation that will get us to thinking outside of the box. Some of the things we already mentioned, creating new definitions in a Grothendieck style, which are not even in the scope of things we saw before. And this is actually what's going to take us toward AGI. So I want to point out that that's exactly the kind of reason. So it doesn't exist, but in this paper from a couple of weeks ago, we basically tried to propose self-improving algorithms which can do it in a dynamic way. So in other words, they can change action space, for example. Usual algorithms, they perform on fixed action space. But one of the obvious things, and I don't know if I'll have time for this, but they definitely need to change their action space and maybe make even more serious architectural improvements dynamically. So this brings me actually to a question to you, Sasha. How much more time shall I budget?
Actually, it's up to you. So we have a kind of informal, so anyone who do not have a time can leave and then see on the YouTube. So it's up to you. Don't hesitate to talk as much as you want.
Would say 20 minutes be reasonable as a
Yes,
plan,
yes.
or it's too much of a horizon?
No, it's okay. It's okay. Sometimes we have, I don't know, several hours. As I remember, when we were students, the seminars by Morozov for quite long.
That's right. So I love those and I miss them, but I don't want to keep people on Zoom for that long.
Okay.
All right, I'll aim for 20 minutes if that's acceptable.
Yeah, sure. No.
Okay, so because here we're basically getting, so yeah, I gave a very long introduction and very gentle one, but this is essentially now the kind of challenge. So that's where, yeah, so we're getting to the serious set of problems. And
Okay, I'm sorry. There is a question in the chat. Maybe let me ask it now. So when you talk about machine learning research level math, like knot theory, what computational resources do you imply? Do you think about corporate like Google or something like desktop?
yeah, that's a very good question. So again, right, so thank you for the question. There could be different ways to answer this question. So when I started working on this a long time ago, I only had basically just a laptop. So I'm a strong advocate for doing, I mean, where we can contribute is doing things with small number of GPUs. One is the maximum for me, actually. So for example, this GitHub repo that I'm sharing, and all these improvements by like 10x is when we have just up to one GPU, very small resources. In fact, if you look at the last paper on this Andrews-Curtis conjecture, it's extremely tiny neural network. It's very small model. It's tiny by especially standards of big corporations. The point is that if we manage to make 10x or 100x improvement in performance compared to research level mathematician like myself, it means that just pouring a lot of resources that Google or DeepMind or whoever has, they can improve it up to 1 million, but that's actually not my interest. So my interest is to demonstrate that it can be done, make a first step and see how the scaling is. And then one can scale it indefinitely. If there is a company which has resources 1 million times bigger than DeepMind, it will do better. And there is no limit stopping it. So my job is to actually try to develop new algorithms and think about how to do it on a very, very small scale compute. So this goes very well with a full accessibility, open source, and small resources. Yeah, very good question. I love it. And I don't want any of us to spend too much time on money on very serious compute. I think if we can manage to demonstrate good performance on smaller machines, on very short cloud time, that's good enough. I think that's perfect. They'll take it from there and they'll improve our models if need be.
Thank you. Thank you.
Okay, so as part of Reinforcement Learning 101, I was planning to give a quick review of some of the, so I mentioned that there are a couple of off-the-shelf or textbook algorithms that reinforcement learning agents use. And this is fairly recent, so that's why everybody is using same 5 to 10 algorithms. I already made a point that that's not going to be enough, but it's important to, I mean, when we start, we have to start somewhere. We cannot immediately dream this interpolation between A3C and TRPO. So let's talk a little bit about what are these algorithms. So one of the first, the ones which are currently still used, in fact, it's still used pretty intensely, is DQN. So this stands for Deep Q Network algorithm, introduced by DeepMind almost 10 years ago. And it literally was trained to play this Atari game. So people who do reinforcement learning, they play a lot of games. So that's the way to think about this whole branch. And this DQN algorithm is basically improvement of traditional non-reinforcement, not AI type algorithm called Q-learning. It's very classical, and Q stands for quality. So basically, this algorithm is analyzing pairs of states and actions. You can think about playing the game of chess, or this mouse is trying to go from top left to lower right to find its home without being blown off or getting some energy along the way. And basically, as it makes moves and repeats these actions, just like when I was solving Olympiad problems when I was a kid, you basically get rewards or punishments every time you make a right step or wrong step. And you populate this Q table of state action pairs with corresponding values. So the only thing that reinforcement learning introduces on top of it is basically a neural net, deep neural net aspect. That's why it's called DQN, which allows you to interpolate to state action pairs that you haven't seen. Because if your configuration space is huge, usual Q-learning, of course, cannot explore all of it. That's why I was suggesting in the beginning, it's always a good idea to estimate like how big your space is. But DQN is very good at extracting lessons for things that you haven't even seen. Right. So then there are, so that was one. Quite a bit later, in 2016, there was this very nice algorithm also proposed by Google. So this is Google Brain and Google DeepMind, A3C. So this is asynchronous advantage actor critic. So that's what A3C stands for. It's 3 A's and 1 C. And that's what we saw on a plot a couple of slides back. It's the one which didn't perform that well on a particular problem that on this learning to unknown question. And this is one algorithm in a whole class of so-called actor-critic models. And it basically, the way it works is that there are several agents. Again, I'll go very quickly over it, that try to explore, make various actions, and they report to one boss who then tries to optimize the overall overarching policy. And they do it in parallel without talking to each other. So that's why they're asynchronous. And actor-critic is hopefully self-explanatory. And advantage, the third A in the name stands for a very particular advantage value function that I won't explain in view of time, actually. So that's a class of models. And TRPO is an example of yet another class of algorithms that used in reinforcement learning called policy algorithms. So it stands for trust region policy optimization, and it does roughly the following. So typical neural net is some version of gradient descent or gradient ascent. But one issue in this kind of basic gradient methods is that you may make a step in the right direction, but if your landscape is very rigged, you can make step in the right direction, but nevertheless too big or too small, and you may fall and never recover. So in comparison, trust region policy optimization does the following. Around the point where you are in your state, it draws a region and explores the most optimal move within that region, and then it continues. So this is much slower process, and in practice, in training, it takes a lot more resources, but this is actually much more robust compared to more naive implementations. In particular, it doesn't have, I mean, it's basically safeguarded against this big falls and big failures. So maybe that's, again, it's not an explanation why in our case, TRPO did better, but you can kind of see why TRPO, this trust region policy optimization, does better. And then there are a couple of variations, which I'm not going to discuss in detail. So there are various algorithms called PPO. That's a version of TRPO. There is also A2C, which is similarly a version of A3C. And the total list is less than 10, probably. So a typical paper on reinforcement learning usually deals with this 10 or so traditional textbook algorithms. But I already made a point earlier that that's good to explore several of them on each given problem. But what we really need for complex problems is custom-made, or better yet, self-improving algorithms, those that can analyze and sort of, again, think about interpolation between A2C and PPO, for instance, in space of algorithms. So let me bring this point home, and in this last 5-10 minutes, basically, that's what I want to do to emphasize that that's what we need to go forward with at least the kind of high-level research math problems that I personally care about. So it's very much like exploring this labyrinth or playing the game of chess, but where the problem is very, very complex. So in the case of Andrews-Curtis conjecture, which is the subject of the recent paper, the problem is to bring, it's kind of like A to B. So it sounds, at first it sounds very much like many things that we already have been discussing. So the goal is to bring so-called balanced presentation of a trivial group to standard presentation, or called trivial presentation. So let me unpack this thing. So you have a group defined by generators, here denoted x1 through xn, and you have relators, same number, which are basically words, r1 through rn, in terms of these generators. If the number is equal, it's called balanced presentation. And somebody tells you that your group is trivial. So we know a priori from some oracle that, yes, this whole thing defines a trivial group. So question is, can we bring, so that's the nature of Andrews-Curtis conjecture, can we bring it to the most obvious presentation where you basically introduce a generator and then immediately kill it using the relator? I mean, basically x1 gets introduced, then x1 gets trivialized and so on, via a sequence of only 3 or 4 basic moves. So there are 2 versions of Andrews-Curtis conjecture. This is called generalized or stable if you include the 4th one, but you can think of them as analogs of Reidemeister moves in the case of unknotting problem. So this is many things are known about this Andrews-Curtis conjecture. It has long history because, again, it's being introduced by Andrews and Curtis 60 years ago. So it's expected to be false. In this case, I think there is a majority vote. There are lots and lots of potential counterexamples, and some of them are not very big. So, for example, this looks very small. It's like only 2 generators and only 2 relations. And this family is completely unknown. So what we managed to do in this recent paper is knock off the most basic and long-standing counterexample from Agbulut and Kirby 85. So it's like 39 years of attempts. It resisted all mathematical attacks. Yeah, so right. So then it has lots of connections to low-dimensional topology. So maybe let me move to this slide and point out that if you think about the group as being fundamental group of a 4-dimensional manifold, you can think of generators as 1 handles in the Kirby diagram, in the Kirby presentation, relators as 2 handles. And then the fact that we're talking about the trivial group can be viewed as discussing 4 manifolds which are homotopy 4 spheres. And what we're trying to understand is where it's, say, literally a 4 sphere. So that, of course, brings us very close to smooth Poincare conjecture in dimension 4, which I mentioned earlier is a very ambitious, exciting problem that, at least on my lifetime, I hope to see some progress. And there are many connections between Andrews-Curtis conjecture and, again, problems in low-dimensional topology that we really care about. So in particular, potential counterexamples to AC become immediately potential counterexamples to SPC4, that's smooth Poincare conjecture in dimension 4. And this sequence of counterexamples proposed by Agbulut and Kirby actually has roots in topology. So these are low-dimensional topologies, Selman Agbulut and Rob Kirby. So that's why some information in this problem in combinatorial group theory actually comes from low-dimensional topology. So good news is that we managed in this recent paper to knock off 1 example, and we are optimistic that in a short time we'll probably do more. That's quite expected. Once you demonstrate that you can move 1 step, then usually it's easy. But that's not the fun part. The fun part is that this problem, Andrews-Curtis conjecture, has the following character. So it's known, this is a mathematical theorem, that you may have very short presentations, kind of one like this Agbulut-Kirby presentations, or there are many other famous examples organized by Miller-Shoup and others that can be very short. For example, take this one, which is written on the bottom of the slide. It has only 4 generators and some relators, so it doesn't look too bad. But it's a mathematical theorem that to trivialize them, and it's known that you can do it, but the number of moves you have to make is hyper-exponential in the length. So in particular, for this one that's on the slide, you would have to have 10 to the 10,000 moves to trivialize it. So that's the minimum. So there is a mathematical bound on the minimal number of steps you have to make. And this is exactly the point I'm trying to make in this talk about high-level research mathematics and why and how it can be useful to AI. So previously in my research, I was basically using AI to solve math, but this is now becoming mathematics informing how to develop new AI algorithms. And that's the main point of this recent paper. So because if I am to make any progress on the Sanders-Curtis conjecture, I know from this theorem, which is almost 10 years old, that I need to deal with these cases. I need to be able to teach RL agent to find such very, very long path. And you can imagine how small probability I have to do that, right? So let's compare this to the game of chess. The longest recorded game of chess has 269 moves. I mean, professional game of chess. So that's very short. And typical game of chess is only 30, 40 moves. So this is much smaller. So previously I was saying, oh, our knotting problems and so on are like game of chess because we have only basic number of moves. That's true because number of moves may be small. Action space is of a small dimension. But if we need to explore such a long horizon of 10 to the 10,000 and maybe 10 to the million and so on, this is definitely much longer, much more complicated than a game of chess. In reinforcement learning, we have to give a reward in the very, very end and then give discounts, right? Have some discounting policy. So it's okay to make a discounting policy on a couple of dozen of moves. That's actually how we do it in practice. On a typical game of chess, when we have only up to 50 moves, that's, you can see that, okay, it's 1% distributed over, I don't know, 50 or 100 moves. But if you have 10 to the million moves, that's a very different story. So question becomes, how do you find, with current reinforcement learning algorithms, such extremely rare events, which are very disproportionate in the reward schedule? In particular, if you are to solve Riemann hypothesis, let's think about like proving it on lean, something very different, not just trying to disprove conjecture, but go from hypothesis to the goal. We'll need a huge number of steps. Again, I have no idea how many lean steps we'll need to prove Riemann hypothesis, but let's imagine that there is a proof or maybe several proofs which have length of 10 million or 1 million or 100,000. If there aren't so many alternatives, then the problem becomes like looking for a needle in a haystack, except reward is extremely high. So hitting any of those potential solutions will produce humongous reward, but hitting anything else will not. So we'll need to teach our RL how to introduce, how to find this black swans. So that's a term that's often used in financial markets for precisely the same reason, that you want to find a very rare event that has disproportionate impact. For instance, market crashes, they don't happen very often, they're very rare, but their impact is humongous. Or extreme weather events like hurricanes, typhoons, tornadoes, and so on. They don't happen very often, but they have very disproportionate, typically negative damage that we want to have kind of control or learn about. So my point is that these are kind of things that we have to deal with in pure math. And if we are to solve problems like the Sanders-Curtis conjecture, we need to be able to divide, not to use off-the-shelf algorithms. Off-the-shelf algorithms gonna do okay, but not great. They have no chance of finding this really hard and interesting things. So the point of this recent paper, so my talk was basically introduction to this recent paper, is that it requires algorithmic development, and that's what the paper is about. This is also what we're trying to do in my research group. So we're currently, so I want to finish with kind of advertisement that we are looking for, we have several positions at various levels of research scientist, postdoc. You can easily find this ads if you look for mathematics and AI at Caltech. And the point I want to finish with is that if you think about it, this is exactly what computer scientists want for developing AGI, artificial general intelligence, kind of thing that can think outside of the box. So not just do well on types of examples that it's seen before, but make steps millions megaparsecs away from what we already know now. So create reasoning way, 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 way outside of the sandbox. So I apologize for running over time, and I think I'll finish with this punchline and advertisement.
Sergei, thank you very much. Very exciting talk and great results in your papers. So colleagues, now don't hesitate to ask questions or remarks. So I'll start with some questions in the chat. So the first question, for the Andrews Curtis problem, what was the action space and what was the space which algorithms are explored?
Right. So I encourage you to take a look at the paper. So action space is easy to describe. It's basically, so these are the actions. So just like for unknotting, this was a set of Reidemeister moves. You ask a RL agent to make one move at a time. So obvious thing here, again, it's a naive thing, was to just start doing this AC, or sometimes called Nielsen moves, which are basically conjugating relators, multiplying them, inverting them, and this is called stabilization move, where you add same thing, xn+1 to the set of generators and relators. So this was basically action space. In fact, I mentioned in the beginning that we had for an Akbulut-Kirby that we managed to solve, we had 12-dimensional action space. Your homework exercise is to translate to see why this, if you only have 2 generators, becomes 12-dimensional action space. So that's actually very easy. But my point is that this will do well. So that will, yes, that will help to get us like off the ground, but that won't be enough to solve more interesting cases like this. And actually, that's what the paper is about. But yeah, that was the answer to the action space question.
Okay.
Oh, sorry. The second part was which algorithms we used. So we used all of the above, everything I mentioned. So TRPO, PPO, DQN, A2C, A3C, we used all of them. So that's a good policy in the beginning. Before we do algorithmic development, try something off the shelf. I always recommend it.
Thank you very much. So, colleagues, Chris, please unmute yourself and ask your question, please.
Oh, I think first of all, Vania was first. I apologize.
Okay, Vanya, please unmute and ask your question.
Can you hear me?
Yes, we hear you.
Yeah. Actually, I want to start with like comment before question. It seems that you're using as actions different moves like Reidemeister moves and so on, right?
Well, for different problems, yes, of course, but yeah.
But actually, it seems a bit uneven because mathematicians do not work in this way. They're proving it in some formal language, and it seems to be more reasonable and like easier to learn an algorithm that will prove some lemmas in a formal language, like and it won't require lots of steps because lots of lemmas in like Durist books and so on require only 2-3 steps, and to do it you have to create another environment that is actually should be based on language model. It is not a question yet. But question is a bit vague. So, did you do something like this? And it seems that a better way to achieve something that will be prove mathematical hypothesis and so on should be some combination of language models that will propose some maybe you mentioned Lean, you mentioned Coq, but it seems that you're not using it in your work, right?
Well, I actually do use it for other purposes. I didn't mention it in this talk, but yes, yeah. But let me let you finish the question, or was it all?
Actually, I'm not sure that it is really a question, but it seems that whole picture is that we should have like language models that propose some like steps. So environment should consist of language model that already trained, fine-tuned on lean and so on. And maybe PPO, H3C, and so on will work well in this environment, because it seems that maybe the question that you're solving right now with these moves is just impossible to solve. So maybe even suppose that even exists some finite algorithm, finitely described algorithm that explains how to unknot any unknotable node. But it can be just impossible to do in with computational resources that the model have. So the question, is there something that can play like this environment right now? And another problem that seems to be the greatest problem in this way is that language models right now has a big problem that they're unable to learn new information. So
Right.
even if they will prove some short lemmas, they won't be able to use it as small steps like human do. Is there something that can solve these problems?
Right. So there are like 4 or 5 questions in what you asked or said. So let me try to unpack it. So, right. First, I do work and have experience with using AI assistants to basically as co-pilots to propose lean steps, for example, to prove hypothesis and so on. So yes, so I'm fine with that. In this talk, that's why I mentioned it in the beginning, but in this talk, I focused on reinforcement learning rather than language model version for such copilot. That's perfectly fine. But there is also a good reason for it. So first of all, let me comment on one thing. In the recent paper, we do propose a finite time algorithms which deal with exactly this kind of issues. So again, I'm not sure that our algorithms are the best, but as a way or step forward toward algorithm development, this is actually what the paper is about. We thought a lot about what needs to be done from algorithmic point of view to overcome this hardness of such examples that may exist in the problem. And that's that. So this talk was basically introduction to that. So off-the-shelf textbook algorithms will not be able to do it, at least with current or simple resources. But our goal was to think hard, and we did it over the course of 1 year, to invent new algorithms which actually overcome this. So in particular, I already mentioned one aspect, that it has to be dynamical change of action space. So you need to start introducing concatenations of moves, and then the actual paper is about how you do it. So the devil is in the details. So that's actual algorithmic improvement. So let me just be clear on that part. So then you're absolutely right that there can be different approaches to trying to solve complex research level math problems, and many people are trying to use language models. And that's totally fine. I have absolutely nothing against it, and I sometimes do that work as well. But in this talk, I just had to focus on something, and I covered a lot of ground, but which may already be too scatterbrained, but I had to be focused on one group of problems. And I like RL because it's kind of self-contained, and it's actually it's a little bit harder to do work here. Dealing with RL models is not easy. So it's usually considered one of the harder branches of machine learning. And it's finicky, it's tricky, it's very sensitive. So dealing with this and then in practice tuning these models is not easy. That's why this area is not very populated. I can easily find many more colleagues who are trying to solve math problems using language models than using RL. So I like to be in the smaller camp simply because it's not too crowded yet. And my hope is that by inventing new algorithms, we can help composing them with language model architecture, such as transformer, for example. So that could be like, we can combine in a modular way benefits discovered in different ways. Also, the reason I don't deal with language models is something that you said yourself, Vanya, that language models are good as copilots, but they can do slightly better outside, go a little bit outside of the sandbox. But currently, as far as I know, they don't go miles away, okay? And that's what we needed here. So to me, it's easier to think about what algorithmic improvements need to be done within RL to teach the model think outside of the box rather than deal with a language model. Language model is already doing what it's doing, and it's hard to interfere with that because for many reasons, but it's usually very complicated architecture such as transformer and such. And it also takes a lot of resources. So one of the questions was, can we do it on one GPU, or do I need to be a CTO of a big corporation? So if I don't have access to resources as a CTO of a big corporation, I'm better off just asking the question in the algorithmic development setting. So that's why I found my comfort zone, and that basically explains why I chose this topic for my research. But there is nothing wrong trying to pursue alternatives. So I think time will tell if in 5 years Riemann hypothesis will be solved by RL, language model. My guess is probably a combination of them. So hopefully everybody will contribute equally.
Hi, I just have two small questions. So for those of us with some compute to play with, if we wanted to experiment or add to this work, like, have you looked into like frameworks for multi-agent systems and mixture of experts or some kind of ensembling? What's your opinion on how such a framework could improve your results? And if you could maybe give us some of your intuition why that would be the case, because as you know, like it's not always clear why ensembling works in certain use cases. And then the second thing, question, I'll just give them both so that we can get them through is your point of creating explosive mathematics beyond the level we currently are. I agree with that a lot, but there's like sort of like two subpoints there. One is like the verification problem. So we create all sorts of statements that are way beyond the base that we currently have. How do we go about verifying those statements as correct? What framework do we use? And then the second is sort of like a soft question, but at the beginning of the CMSA proceedings, Mike had made a comment that we should sort of be wary of cargo cult science. I think that's a quote from Feynman, and I take that to mean, and this might be wrong interpretation, that we to have all of be inundated by all of these potentially well-formed and potentially correct statements that we haven't verified. Then we start building theories around them. Like how do you see like the field of mathematics? And I'm not a mathematician, but I'm just kind of curious. I'd like to know, like, changing with like a mixture of AI generated statements and human generated statements, and in the situation where maybe AI generated statements are much more than human generated statements. Like, what is the job of the mathematician 20 years hence? And that's it.
Right, so let me answer the first question. I apologize, I'll probably have to ask you to unmute again and we discuss the second one because I understood it a bit less. But regarding the first question, so you mentioned multi-agent models. So that fits perfectly with this framework, how to develop new models that can basically, the term I like to use is learn how to learn. So there should be almost like another model on top of the traditional model, or maybe some ensemble of models that teaches whether it should be, I don't know, PPO or A2C and things like that. So, right, regarding that, I think the way one can contribute, and I encourage everyone on this meeting to play with this, and there is, of course, a way to contribute. So depending on our level of skills and resources, one thing that it didn't occur to me back in the day when I was basically doing this on learning to unknown project years ago, is that I only looked at the positive trend here, that TRPO does well, we celebrate, we move on. That's super exciting, right? So, but now the way I look at it is precisely through the lens of the question that was asked earlier, why? So in other words, we need to really understand why this blue thing is going up and orange thing is going down. And so therefore everyone can contribute. Those who are not very comfortable dealing with multi-agent models and algorithm development, I will encourage people to try off-the-shelf textbook algorithms on their own mathematical problems and ask these questions and produce analogous graphs, as in this Learning to Unknown paper, just to see what works and what doesn't on different kinds of problems. That's actually very useful. It will help mathematics, but it will also help us build a knowledge base for which algorithms align for which particular tasks and for what reasons. So that's going to be super useful. We're still in the very, very beginning of this journey. So basically trying different algorithms, even off the shelf. But then something you mentioned is very cool, is actually what I'm trying to do in my group, is indeed experiment with either evolutionary algorithm or multi-agent algorithms, things that are more dynamic in their approach. And community of people who do this on mathematics is even smaller. I would say it's like probably less than 5 people in the world, unfortunately. So the more of us, the merrier. So in my group, for example, we didn't have even bandwidth yet to play with multi-agent model on this Andrews-Curtis conjecture. So this is something on our to-do list, and I would encourage everyone. So thanks for bringing this up, but I mean, there are definitely a lot of potential to contribute simply because, yeah, try for example, multi-agent model on this AC. Maybe I'll be at CMSA next week, so let's discuss this. And it would be great to do lots of experiments because nothing has been done. I mean, we're just starting to explore this territory. So your second question, so hopefully I covered this, but your second question was on formalization of math, and I'm not sure I fully understand the context and the question in part because I was not present during that quote, so I'm not sure what the context was. And yeah, would you mind repeating it? I don't know if we have time for this discussion, but
No, maybe this is just too soft, but I mean, and maybe I'm not understanding your program entirely, but like, even if we get a bunch of solutions that these algorithms generate, we have to still hand verify them to some degree, right? And then
no.
no,
I mean, if
okay.
yeah, that's the beauty of it. So if RL finds a path which connects say unknot to some complicated diagram, that's it. I mean, this path itself, if it found it, if it's demonstrated, that's already 100% rigorous. So that
Okay.
in this context, that's done. So that's, I think, yeah, I should have emphasized. We had a paper with some colleagues called Rigor, and it has Poincare conjecture in the title. And the point of the paper was precisely that. So using RL for these things is useful because it doesn't have any stochasticity. So it's not like language model. It doesn't, I mean, language model may produce something that we need to verify. This is very different. If it finds a path, it is a path. It found it. Question is how to find it.
Okay, then the rest of the question is moot. But yeah, the context is not relevant. But I think the first week there were some comments made about, like, if we had a bunch of generative algorithms creating mathematical statements, and then we have a bunch of mathematical statements that are that we haven't verified, like, but then maybe some people start using them to build theories or something. This would not be a good situation, even if we build, things of that nature. So
okay, now I understand. Yeah, so so this is very common, of course, and big discussion of interaction of informal language models and formal language models, that are islands of what's true, what's not, and so on and so forth. Yeah, this is very different. So that's why it doesn't relate to me directly here in the talk. It's more relevant to using, for example, something like LLM or generative model indeed to propose a solution. But the reason I like RL is hard in many, many ways, but good thing is that if it found a set of moves which either won or lost game of chess, we know what happened. We know that it lost or it won. And for example, in this recent paper on Andrews-Curtis, our proof is very short. We basically give the sequence of, I don't know, 50 moves, which closes the goal, and that's it. I mean, we just write it. So what the difficulty over the 40 years was to find a sequence, and that's where RL was helpful. So how to do it and so on and so forth is complicated thing, but once you have it, it fits to, I don't know, half a page. You just exhibit it, and that's it.
Thank you. And the paper that you're referring to was called Poincaré's, the one that showed that the path is precisely rigorous.
Well, sorry, I mentioned two papers. There is a paper in Nature Communications called Rigor, and it has Poincaré in the title. So that
Okay,
makes
I'll Google that.
How RL does not further verification. But I also referred to the more recent paper about, it's called, I even forgot what it's called. What reinforcement learning finds hard in hard math problems or something like this. So that's about this Andrews-Curtis conjecture, where we managed to solve one of the long-standing cases. And I'm just saying that the proof itself was there. So the paper has a section called proof of the main theorem, and that section is only like 1 page. So it has lots of comments, but the gist of it is exhibiting the sequence which closes the goal.
Thank you. I'm looking forward to next week.
Yeah, thank you, Chris.
Sergey, do you have some time? Because there are some questions in the chat. Is it okay?
Yeah, but I have another meeting. It's good that we did some time balancing in 15 minutes, so I have to go, but I can maybe stay for another 10, 15 minutes. And
Okay,
thank you to
I
everyone
think
for sticking around for that long. Yeah, thanks
okay.
to everybody.
So the question is, so as far as I understand, this is about RL algorithms, and what do they lack right now? So why not enough?
Right. So the algorithm development in RL is by like everything in AI, fast developing subject. So of course they are being developed and so on. I think the problem is sort of twofold. So in computer science, if there is a very technical, challenging problem, like the ones we're trying to attack, usually research scientists develop their own algorithm for a given technical problem. So there is a huge gap between a professional mathematician who understands what needs to be done, but doesn't know how to code in Python, and computer scientists who is comfortable with algorithm development, but and they do it for robotics or other areas, but they obviously cannot speak math language. So part of the challenge here is actually educating both communities and building this gap. So unfortunately, even at present day, there are still very few people who comfortably can and meaningfully contribute both ways. So I would say that that's why starting with something simple and playing with this is very useful, because community is still very small, unfortunately. It's tiny. So we need definitely more human resources to push this forward. At a more technical level, what reinforcement learning algorithms are lacking is precisely this ability to be adaptive, dynamical, and change their not just hyperparameters, but the entire algorithm in a very sort of big major ways. So I use this term interpolating between A to C and PPO, but again, this doesn't exist at the moment. So that's what we're lacking. And in this more recent discussion after the talk, so Chris mentioned the multi-agent model. I mentioned this evolutionary algorithms and so on. So these are kind of first initial baby steps in that direction. But even in RL community, that's something, I mean, pretty cool, cutting edge. And as far as applying them to math problems, this just has not been done. So this recent paper on Andrews-Curtis, the reason I'm excited about it is not because we solved some long-standing case. This is cool, but this is not the source of my excitement. My excitement is because we're starting to make steps into these new directions where algorithms can make dynamic changes. And this is just in its infancy, unfortunately, especially applying to math.
Okay, thank you very much. There is another short question from Stan. Is the algorithm space a metric space?
Well, I have no clue, and I'm glad that talk did the right job. So it encouraged people to think, no pun intended, outside of the box. So I don't even know. I mean, I use this term like space of algorithm very figuratively. Luckily, people, it ignites questions precisely like the one from Stan, but I don't know. And I think it's important for us to start thinking about it. So maybe if we start thinking about it, 5 years from now, we'll have an algorithm that has ability to interpolate. But my issue, and that's what we're lacking, is that until so far, aside from computer scientists, those of us who are using it for math did not even realize that this is a question, or that we can ask this question. So anyway, sorry, the short answer is I have no clue, but we should think about it.
Okay, thank you. There is a question from Olga Nikitin. Olga, maybe you can unmute and ask by voice. How would you prefer? Or I can read it.
Okay, but
okay.
I can read it to maybe it's not clear. It's related assumption. There was a question about, you asked if there were questions about that every problem have decision as path from A to B, and is it possible to relate with RL that and Markov chain process, that when we find this path from A to B, every step for solving this problem, it doesn't matter how we get to this step, how what decisions we made before this step, and it's important for us now. It's only best decision on current step. Sorry, I am new by it. If you think that it doesn't make sense, just skip it. But thank you.
No,
Okay,
I think it does.
Comment, Sergei. So it's related to our problem finding on the Kelly graph, and that's a kind of Markov property. So if you came into some node and you want to go to the destination, it doesn't matter how did you came to this node. But actually, this is kind of sometimes matters, because if we use machine learning model for prediction, then if this machine learning is far from being perfect, then history matters. If you come to the current position making bad nodes, and now just one by chance you have one good direction, maybe just by chance. Yes, so you maybe okay, maybe it's I'm not very clear, but again, I think the question is about sometimes we have a kind of Markov property, and it doesn't matter how you came at the current position, but sometimes it matters. And so in the generality where you think, do you think this kind of, do we have Markov property always or not?
Right, I'm not sure I should speak about Markov property in great generality, but yeah, so whether it matters how we got to a given state, I think the answer is certainly yes. So in particular, again, I care about this very like complex problems where in a game of chess it will be, I don't know, millions of moves, millions of, I mean, it's a super long game of chess on infinite chessboard. Think about it this way. So of course, to me, I'm a very concrete guy. I just want to have conjectures solved, theorems proven, and like Riemann hypothesis. So it probably does matter a lot. And at every stage in development, I mean, we should think of where to, optimize resources, cut corners, and then do better in terms of resource use. So if there are like super long paths which take us to a given state versus shorter ones, of course, it's beneficial to use shorter ones. So if I understand the question correctly, then the answer would be yes, that it matters a lot. right? Whether
Okay, thank you.
But maybe I'll be happy to discuss this more later to also understand better connection with calligraph problems and other things you have in mind. So I think there could be a lot of basis for it.
I understood that we have decision as a path from A to B for every problem. It was in beginning of election, and I was trying to relate it with REL, and I understood that I was wrong. So thank you for your answer.
I'm not entirely
we
sure.
We cannot think about path about solution as a path from A to B as a Markov process, chain process. Okay.
I'm not entirely sure. Yeah, let's discuss this later. So I think, yeah.
Okay.
But in any case, in the talk, indeed, I try to advocate or point out that kind of sadly, it seems that proving theorems is from A to B, from hypothesis to the goal. Finding counterexamples, as I illustrated a lot in different problems in this talk, is also, or examples, is also searching for something, and it's typically searching for a path. So now I have this kind of mental game that if somebody gives me, so I think Fodor was asking a really cool question, like, can a computation be thought of as a finding path? And maybe it is, because computation is a sequence of steps. But anyway, I think this is more exotic version of finding path. But now I have this mental game I try to play with myself, that if I don't know, hear someone talking about math problem, I try to think, oh, can it be formulated as a finding a path? And a path of what? What kind of steps? For example, Fodor was talking about calculation. So is it, I mean, every calculation is a sequence of operations, addition, multiplication, and other more complex ones. So it's probably still a path.
Okay, thank you very much.
Okay, there is one more in the chat. What are your suggestions for architecture short for LLM like GPT?
So what are my suggestions for architecture
search for LLM like GPT?
Architecture search. Yeah, so this is much more complex. And like I say, this is actually quite far from what we're discussing in the talk, because AI focused on algorithms, not architecture. So that's a very good question. But another reason the question is somewhat complex, so I don't think I have a good answer, but it's complex because, again, if it's asking about LLM, that's already adding many layers of complexity, because first L in the LLM is large, and the talk was about small resources. Also, most of the language models involve fairly complex starting points, such as transformer. And again, this is yet another layer. So I don't think I have ability to meaningfully answer this question in a short time, but let me think about it. And I encourage the author to write email to me. I'll try to think about it, and maybe in a couple of days have much better comment or something to say. At this point, I don't think I can give meaningful answer.
Okay, if you have time, there are two questions more in the chat. So first, Artyom, you can unmute yourself and ask.
Okay, thank you. Do you hear me clearly?
Yes.
Okay. First of all, thanks for the talk. Really nice to hear the sequel if possible. Well, to the question, maybe I just missed that, or maybe I wasn't able to formulate it for me to understand. Because right now I don't even understand in principle how it's even possible to train on a reward that's so difficult to achieve. And there is no like rewards in the middle of our problem. Like, do we train maybe the model on something much easier before that to get something like mathematical reasoning for the model in the context of a specific problem? Thanks.
Right. So I apologize. I have to run in a couple of minutes. So this probably will be, unfortunately, the last question I'll be able to answer. But yeah, let me try to get that answered. So yeah, so let's think about, for example, this concrete problem of Andrews Curtis, and that's a good illustration of a very hard problem that usual traditional algorithms that I mentioned cannot easily solve it. Part of the reason is that, yes, they have to find this needle in a haystack or black swan type event, which is very rare, but extremely hard to find. It's just a super long path in a space of all paths that it has to explore. So traditional algorithm has no chance. I mean, given the given resources. So one strategy which we explain in a paper, we explain a couple of or like variety of strategies, but they're all centered around one idea. So first step is obvious. So in order to do something like this, you have to have dynamic action space. So in other words, you have to have ability to add new actions. And this will be very clear in a second that it will unblock this issue. Why? Because, for instance, if after a couple of epochs, you learn that for whatever reason, policy is explained in more detail in the paper, you should add an action which is concatenation. So a new move, which is say 100 of basic moves. So that's already good, because if you iterate this process, you have ability to go exponentially. So after another few epochs, you learn that, oh, 100 of those concatenated moves and so on and so forth. So that's obvious. That's the first step. That's actually not very new. That's been already used a number of times in many things. But main devil is how you do it. And that's what the paper is really about. So we argue, at least in this recent paper, that in order to do it, you should pay attention to hard cases which were solved at every step. So in other words, somewhere, for example, if I show you some of these graphs that show performance as enrollment of epochs and learning process, we should focus on things which are hard. Not in other words, not celebrate what's done, but focus just at the borderline cases, which, for example, in this graph, which were not solved, or this is even better, were not solved at the previous step, but are being solved at step n. And then think about these hard cases. Basically identify what's hard and focus on those and use that as part of the policy making decision for which steps need to be added. And also one has to remove steps from the action space. So anyway, in the paper, we propose this addition and removal of actions from the action space based on notion of hardness. And much of the paper is how exactly to identify what's hard, what's useful. And that's basically a way to produce finite time algorithm that can actually unblock this hyper exponential paths. So again, I very much appreciate all the questions that's being asked. I'm super grateful to Sasha for inviting me, but I'm afraid I have to run, and I'll be glad to answer questions via email or otherwise.
Thank you.
Thank you very much, Sergei. Thank you very much. A great talk and exciting results. So, colleagues.
Well, thank you all. Thank you all for coming, and thank you all for questions. Apologies if I wasn't able to answer any.
Okay, thank you very much. So video records will be on our YouTube channel. I put in the chat the links. Thank you very much, Sergei. Thank you.
Thank you.
Bye-bye. Bye-bye, everybody.
Goodbye, goodbye.